Okay, I guess we'll start. So when you get home, what's the first thing you do to relax? You turn on Netflix, right? Everybody? Yeah, okay. Pick out your profile. You get to your homepage. You might see Iron Fist at the top, or scrolling around, you see Sandy Wexler. For those of you who like Adam Sandler, it's okay to like Adam Sandler. I like Adam Sandler. A lot of people at work give a shit for not. Anyway, so Chef's Table, I actually really like cooking. I enjoy this show quite a lot. You can search for all the different Marvel shows that we have. There's a whole slate coming out. The Defenders are coming soon. I swear this isn't an advertisement for Netflix. But you finally settle on Narcos. So you're watching the first episode. You get to the point where he tells the guard, "Me llamo Pablo Emilio Escobar Gaviria." He tells them "plata o plomo." And you just thought this part was so amazing and so awesome that you had to go give this show a thumbs up. It's now thumbs, not stars. And you've been showing all of your friends all the different parts of the episodes that you actually enjoyed, so you can see we're keeping track of where you are in all these different episodes. Okay, does anybody have any guesses on how long we have to capture your attention before you decide to go do something else besides watch Netflix? Just throw it out there, anything.
8 seconds.
8 seconds is a little low. 30 seconds is also, it's about 90 seconds, so it's about a minute and a half. So the faster, the smoother, the easier it is to find what you're looking for, the more likely you are to stay and continue watching stuff on Netflix. One of the ways we keep things fast is to introduce caching. So in that experience that I just showed you, there's a lot of different things that caches touch. So signing up or logging in, picking out which profile. Whenever you sign up for the first time, we'll ask you which videos that you might like or that you know of. The actual personalization process, which we'll look at in a lot more detail later. Loading the homepage, scrolling through the homepage even. Any A/B tests you're a part of, and since everybody's part of a dozen or more at any given time, you're a part of them. And even picking out which specific box shot to show you involves caching. And there's a whole mess of other things besides that I haven't even talked about that have caches involved, and a bunch of them you can see even have multiple caches involved. Put another way, this is what a typical homepage request looks like. So this is the output from our request tracing system called SALP, and the homepage request comes in from the left and fans out to all the different systems in here. There's a couple more layers, but it was just like a line, so it wasn't very interesting. And you can see there's a whole ton of leaf nodes on the right side, and out of all those leaf nodes, there's maybe half a dozen in this picture that are not a cache node. So you can see one normal, seemingly innocuous request can turn into many different requests. So my name is Scott Mansfield. I'm a senior software engineer on the EVCache team. Presenting with me today is Vu Nguyen. He's also a senior software engineer on the team. So I'll take you through some of the basic architecture, use cases, and some extra things we built up around the product to make it work inside Netflix. And then Vu will walk you through our use of RocksDB to save money. So what is EVCache? What does it stand for? It's ephemeral volatile cache. At this point, it's kind of a misnomer for reasons that will become apparent in a minute. In its core, it's a key value store that is optimized for running on top of AWS, and it's tuned for Netflix use cases specifically. It's a distributed, sharded, replicated key value store. That replication is tunable both inside a single region and across regions, because we operate out of 3 regions in AWS. It's based on memcached, and it's highly resilient to failure in the cloud environment. It's also network topology aware and linearly scalable on the server side. And we can do seamless deployments for our customers. So we do deployments all the time. Nobody notices anything. So I'm going to take an aside. Why do we actually want to optimize for AWS? For those of you who may not be familiar with the vagaries of working in the cloud, instances can just up and disappear at any given moment. And this happens to us all the time. Entire availability zones can fail. Maybe a data center has a power outage for some reason, or regions can become unstable entirely. Most of the time, this is us shooting ourselves in our own foot, but it has happened where AWS causes some problem, say DynamoDB or S3 is down, and that's something we just have to deal with as a system. The network itself is also just lossy. It happens, especially between regions. Customers in the real world can actually bounce between regions very rapidly with their different requests. And the simple fact of life is that failures happen. Shit breaks. We have to be able to deal with it. I'll give you a sense of scale for EVCache use inside Netflix. So we store hundreds of terabytes of data in EVCache. We do trillions of requests per day. There's tens of billions of individual items stored in the cache, and those are accessed with tens of millions of requests per second. We do actually millions, in the single-digit millions of cross-region replications per second. And that system we'll take a look at in more detail later. We have thousands of servers, more than 10,000, not really enough to call it tens of thousands. We can have up to hundreds of instances per cluster, or hundreds of microservice clients talking to a single cluster. We have tens of distinct clusters, separated out mostly by separate use cases. We do this across 3 different AWS regions, and we have a team of 4 engineers. Okay, so let's talk about some basic architecture with just one client, one server for right now, and then we'll expand from there. So a client normally is an application that is consuming another team's client library, and that client library is actually our, it's their team that we have a relationship with, and they consume our library. On the server side, we have a big fat memcached, or at least something that looks like memcached, that's alluding to our use of RocksDB, of course. And then a sidecar that we call EVCache, and that's our Java sidecar. It's a small process, and it's our hook into Netflix, basically. That's the only Java thing, and most of Netflix is Java, so we have that running for a couple of reasons. One of the reasons is actually to register. These actually have a direct connection. There's no intermediary, there's no load balancer, there's no nothing in between them. It's a direct TCP connection. One of the reasons we have a sidecar is to register with our service discovery system, which is how the clients actually find the servers in the first place. And that's called Eureka. That's used by everybody at Netflix. So expanding out to a real cache cluster, we have a replicated copies of the data. So in this picture, you have 3 zones. You have 2A, 2B, 2C. Each one of them, you can see there's this little dotted line around it. And that is signaling a copy of the data. So in this picture, we actually have 3 copies of the data spread out over 3 availability zones. And you can see the client talks directly to every single one of these servers. And if we have multiple clients, all of them talk to every server. And this ends up forming what's called a complete bipartite graph. So each half is completely connected to the other half, but they're not actually talking to each other at all. So more importantly, there is no connection between these servers at all. So for reading, this is where the topology aware part comes in. It'll first try to read in the local zone. And if that fails for whatever reason, we have 2 backup paths that we can try. By default, we just try once more, but we can configure it in any way we need to. And this is what a lot of people get hung up on, is the actual writing process. So the writes are fanned out from the client to all the different copies. So in this case, we have 3 separate copies. If a client in US West 2A wants to write, it actually writes to all 3 of them. By default, this is asynchronous. People can just drop the future on the floor if they want to, but some people can choose to block. So the same thing goes for the other clients. If any client wants to write, they all write to all the copies. And in this case, if 2B writes to this middle box right here, and 2A wants that data, it'll then read from here first, and it'll see that local copy. Okay, use cases. This is where it gets more fun. There's going to be a couple ones that seem familiar, and then a couple that might make you cock your head to the side a little bit and wondering why we're doing that. So the first one is Lookaside cache. This is very straightforward. You have a cache in front of a database because the database isn't scaled to handle the load of your customer requests. So the application that we saw before and client library we saw before, EVCache client we saw before, in this case, it'll ask the EVCache client, do you have that data? It'll go to the cache, check. If it doesn't have it, it can go to the server now, and that server can go to its backing storage or do whatever it has to. Typically, the storage for us is Cassandra clusters. And then the server's responsibility is to write back into that cache either concurrently with the response, or they can block on it if they choose to. So in that case, it would be something like subscriber information, where we would have a separate like Cassandra durable storage mechanism. In this case, you can think of it like session storage. Whenever you're watching a video, you have a watching session effectively. So whenever you click play, for example, you would have something start a session. And as you're watching, we're sending back bookmarks and pinging Netflix every minute or so. And then when you're done watching, we'll do like a session roll-up and maybe write it to somewhere else. So in this case, it's like just a session storage, a transient data store for that information while you're watching a video. And there's no Cassandra in this picture, right? There's no persistent storage otherwise. People rely on that replicated nature of the cache in order to have that data available. So this is where it gets a lot more fun for us. So we actually are the primary storage mechanism for a bunch of data, and the data itself is the personalization data. So every single night, every profile on the service gets a brand new homepage generated for them. This is a very large-scale batch process, and we'll take a look at it in a little bit more detail in a couple slides, so you get a sense of how the system works together. So here, the offline batch processes will write every night into the cache, but the online services, they're just reading from the cache. There's no like sense of when these things are running. It's completely asynchronous between the two, and we have a strong culture of fallbacks. So that means if you are a brand new user, or for some reason you can't get that data, we have something that we can serve you that's better than nothing for your personalized homepage. So that prevents us from cache misses or cache failures from actually like completely taking down the service. But those are rare occurrences. It's just they exist for that small percentage of failures that do happen. So the full picture looks like this. We have this offline compute, the online service is running, and there is a cache sitting in the middle, bridging this gap between our offline batch systems and the online systems that are serving customer requests. This is where we're going to talk about RocksDB, just so you know what's coming. I'll run through the next one a little bit quicker. So this is very similar to the last one, except we now have this extra control system to the side called Valhalla. This is not a system that we own. It's something that somebody else has built that uses us. So it's very similar to what we had before, where we have an offline compute system writing into the cache, but now this control system here is like triggering it every so often to write new data in. And then it'll tell this service over here called Archias, or dynamic properties, and that's used to dynamically configure applications at runtime all over the place. But what it does is it tells that dynamic property service, here's a new version of this data, and the application can read that property and start reading that set of data. But now we want to like do a step forward and put out a different set of data, and Valhalla will trigger another compute, write that red version, and then update the property. Clients pick up on it, and then they can start reading the red version. I won't use the word atomically because this is a database conference, but mostly at the same time. Within about 30 seconds, they've all flipped over to the new set of data. There's also a few places where we need really high volume, but also extremely high availability. So we tend to do extra layers of caching here. Think UI strings. If you don't have like the strings in the UI, you may have to like reset your Apple TV, which is not a great customer experience. So let me back up. This is an application requesting from the client library, but then we actually have a local in-memory storage mechanism that we keep in our client, and we can configure that. We also have the ability to mask failures in either our cache, the remote cache, or a remote service by being able to background refresh data that's about to expire in our current in-memory cache. There's a couple places where it's extremely important that we have data, even if we have 5-minute old data, it won't matter. So that is typically a very high hit rate. Then they have a remote cache, and a lot of teams will have this process that computes and pushes data into the cache, say every hour or every half hour, something like that. And then, of course, we have the same pattern we saw before, where we have a server and a database, but I actually don't know. I think there's still one team who's using that, but most teams have actually found that whole part to be optional. Because they have this compute and publish on a schedule, they find the EVCache uptime to be sufficient for their use case, especially when combined with the in-memory storage that we have in our client. Okay, so I promised more of a like an overall system view of the personalization process. By the way, if anybody has questions, feel free to ask them while I'm speaking. It's fine. So remember that one like pre-compute writing into the cache and then the one application reading from it. So that might be one of these. There's a compute system. It's an offline batch system writing into the cache. So this would be like compute A, cache A. And then you might have B. These are sourcing data from Hive or some other offline storage mechanism. And then you might have C, which pulls stuff from offline, but also depends on these algorithm outputs. And then you might have D or maybe E, and you end up having this not really formalized, but informal data dependency DAG that gets formed between these different teams. And these are output into different caches because the output of, for example, E here is not the end goal. The output is of all these different stages is the end goal. So we might have, these are all offline, right? We might have these online systems that pull data from several different places to do their task. And we might have other online systems that pull from different sources. So this ends up being somewhat of a complex web. There's not too many of these, so it's still attainable to hold it in your head at one time, right? But it does end up being this complex set of data dependencies in here. Like I said, it's not formalized, but this is just what happened. I always forget the name of the law for this, where the systems organize themselves like the people are. Okay, so there's a few things that we've had to do besides just running the clients and the servers to make this thing work in the Netflix ecosystem. Like I said, there's cross-region replication. There's a couple other things we do. So we actually run Kafka in parallel. We publish a metadata stream about the mutations that we do on the cache into Kafka per cache. And that unlocks global data replication and metrics for consistency. We also have this feature that we were heavily involved with adding into memcached, where we can iterate through all the metadata in the cache about all the keys. And that allows us to do things like cache warming or doing instance recovery. Whenever one instance dies, we want to refill that particular instance or complete backup and restore. So I'll talk about one from each of these. So for Kafka, we'll talk about the global data replication because this is definitely the more important version. So we have 2 regions. This example is just between 2 regions, but we actually have 3. So this is like a triangular thing in the real world. So we have an application in each one reading from this cache. You have 2 caches that are meant to look the same in both regions. So when we do a mutation here, we'll actually publish this to Kafka. Well, when we do a mutation, we publish the metadata about that mutation into a Kafka topic for that cache. And we have an application that we call a replication relay. And that relay, what it does is it'll read that stream, potentially read that data if it needs it to publish across the regions, and then post that over an HTTPS link to ourselves, another application that we run called the replication proxy. And that proxy will perform that action on the cache in region B on behalf of the application in region A. So that proxy will actually do that mutation on the cache in the other region. And then the data is visible in that region to the other application. And of course, this goes both ways, or with 3 regions, all 6 ways. Okay. So for key iteration, this is actually really great for us because it unlocked a whole lot of new things for us. But I'm going to talk just about cache warming in this case. If you're curious about the other ones, I have slides on those, but they take some time to go through. So let me know at the end if you actually want to see those. So for cache warming, say we're in our steady state here. We have our small 2-node cluster. Everything's fine, but now it's getting a little full. So we want to, before it gets completely full, double the size. So now we want to add a 4-node cluster. So what we can do with our client is bring up an empty one and just start sending writes only to that new cluster. And that is how we used to do deployments entirely. So after the entire TTL ends, you can flip reads over to the new cluster and they look the same because all the old data has left. But we wanted to accelerate that. So with this key iteration, we can bring up this control application that will ping the servers in the old cluster to dump the metadata about their cache contents into S3. So now that we have this metadata, we can bring up a Spark cluster with a Spark job. It reads this metadata, and in a distributed fashion, we'll pull the data out of the old cluster and write it into the new cluster. And all the while, we're getting writes from the online application as it's running. So we're not actually missing anything here. And that'll make the new cluster look like the old cluster by the time we're done warming. And at this point, we can flip reads over to the new one, and we'll just tear everything else down, and we're in a new steady state with double the cluster size. It used to take us, for some caches, 4 weeks to deploy, and now that's down to a matter of hours. Yes?
Aren't you using any of the eviction mechanisms provided?
Yeah, that's one of the idiosyncrasies, is generally no. We tend to keep it so that things TTL out versus get evicted. We do use them in the next topic. You'll see in a second the new server that we're talking about that has RocksDB as disk storage. We do use LRU there. But for most people, they actually don't want things to be evicted.
So you're using this as a in-memory data store?
Effectively, yes. That's why I said it's... Sorry?
Instead of cache with evictions or something, you're using it as an in-memory data store?
Yeah, so that's why I said at the very beginning that ephemeral volatile cache is really a misnomer. It's kind of the opposite. Okay, so thank you for the transition, because we're going to talk about the server that actually does use the LRU mechanisms of the cache. So this is, we're switching gears here a little bit. This is a project that came up last year that has saved us a bunch of money. And this project is an optimization project for us. So the project is called Moneta. So why is it called Moneta? It's named after the goddess of memory and also the protectress of funds for Juno. It's an evolution of our server side, like the actual server itself. And it's a cost optimization, like I said, but we just basically put some data on disk. And that has actually lowered our current costs, but on top of that has lowered the slope of the increase in cost over time as we continue growing. So it also has knock-on effects. It's not just like a one-time thing. And it takes advantage of the request patterns that we have globally between the 3 different regions. So our old server is, in the grand scheme of things, fairly basic. We have a big-ass memcached process holding everything, and our sidecar, which is our hook. And that's about it. All the data is stored in RAM and memcached. And so at the beginning of last year, though, what happened was we switched to a global N+1 architecture with our 3 different regions. So every region, in theory, can serve every customer exactly the same way at any time. And that meant we ended up with a whole lot more data. So this started to become very expensive. A whole lot more data because of replication between all the different regions. So global data meant we have a whole lot more copies. But the access patterns themselves are very heavily region-oriented. So if you're watching here, you're going to be hitting US West 2, and the likelihood that we see you in EU is really, really low. But we do need to have that data just in case. So in one region, hot data is very hot, cold data is very cold. So we'll store the hot data in RAM, in memcached, and the cold data on disk in RocksDB. So at that point, we can kind of size the RAM for the hot set and the disk for the full set. Now we have units of like one Amazon instance, so we can't like dynamically size these individually, but this is the basic concept. So this is what our new server looks like. There's a couple projects that went into this. There's one called Rend, and then there's another one called Mnemonic. So Rend, I will go over, and then Vu will pick up at Mnemonic, and then go over our use of RocksDB in that case. So from the outside, though, it's kind of important. This looks like memcached. This server can be changed out with a memcached-based server, and nobody knows any difference. It just looks like a much bigger server that can store a whole lot more data. And we still run memcached here for our in-memory storage because it's still great at what it does. There's no reason to drop it. So Ren, if there's is there anybody here who programs in Go? One? Okay. Okay, a couple. So if you're a Go programmer, you'll recognize this command line. This is an open source project on our GitHub page. You can go get it if you feel like playing with it during the talk. That's fine. It's a high-performance Memcached wire-compatible proxy and server. And this is what allows us to switch out the servers without any changes to the clients. Although we did do a change for optimization purposes. So it's written in Go because of the concurrency primitives that we get. It's very easy to just do like one Go routine per connection. And it's just productive for developers. It's fast running in production. Vu will show you our latency numbers in a minute. And it's just easy to deploy. Everything's a static binary. There's a bunch of different reasons. So what is its job? It manages that relationship between the L1 and L2 parts of this cache. And from the very beginning, we have some caches that have tens of thousands of concurrent connections. So it had to be one of the design like inputs was you have 20,000 connections running concurrently. So the project is actually just a bunch of libraries. We used to run the actual main file. It's in GitHub, but we don't anymore because we merged a couple processes together. But it is still runnable. It still functions. And the rest of it we actually use as a bunch of libraries. So it manages the connections from the outside, the request orchestration between L1 and L2, what sub requests do you send where. It actually includes a metrics library that was custom written for this application, not because it was like a great idea to write your own metrics library, but because there's no Go open source libraries that integrate with our Atlas metrics backend. There's a particular thing in the Java client library called a percentile timer that allows you to get cross-fleet percentiles within a couple percent error. So with this metrics library, we can actually see in fine detail what our latencies are like on the server side, which is something we didn't have before with Memcached. It just doesn't have latency metrics. Uh-oh. Okay, we're good. There's multiple orchestrators for those optimizations that I mentioned earlier. There's a feature there called parallel locking, so no one key can have two mutations happen on it at the same time. That's opt-in. And then there's a very efficient connection pool to talk to Memcached in the background. Okay, so Vu will take it from here, talk about Mnemonic and the server, some latency numbers.
So Mnemonic. So Mnemonic is responsible for managing the data storage on SSD, and of course it uses RocksDB to do that. It uses the Rend server libraries to handle the Memcached parsing, and then it maps the Memcached operation request to the RocksDB operations. For our use cases, we have writes happening all the time. We need our random reads to be fast enough during the write load. Fast enough for us is under 20 milliseconds, and the important thing also to be under 20 milliseconds, but to also be very consistent, so not to have spikes above 20 milliseconds too much. Our write load generally is going to be higher than our reload at this level where we use RocksDB. And that's going to be partially because of our local Memcached process on the box. The Memcached process will handle most of the read requests. So and so only a smaller fraction of it will be handled by RocksDB. In general, we can predict the amount of memory that RocksDB is going to use, given our knowledge of our use cases. And that allows us to separate our usage of Memcached and RocksDB into separate layers. Memcached will be our L1 cache, and L2 and RocksDB is going to be our L2 storage layer that's local. And this separation allows us to do a special optimization, and that takes advantage of our region-oriented access patterns. I'll give you some more detail on that in a couple of slides later. So how do we use RocksDB? Actually, we do not use level compaction. We tried level compaction initially with our batch compute load, where our data sizes in that case are about 20 kilobytes per record. But we encountered some problems. The level compaction process was generating too much read and write traffic to the SSD, and that caused our read latencies to be unpredictable. our latencies far exceeded our hopes of being 20 milliseconds. We were seeing sometimes close to 80 or 100 milliseconds. We also don't use the block cache. Instead, we rely on the local memcached process. We expected that to be more efficient because only the records that are popular would be in memcached. We wouldn't have to carry along with it the unpopular records that just happen to be on the same block in RocksDB. And we also don't use compression. The reason is that our client already compresses the data and before they send it to our server. And so recompressing something that's already compressed isn't helpful. And we don't have enough CPU power to uncompress it and then recompress it again. So that's a limitation that we'll go over a little later. So what do we use is FIFO compaction. In the FIFO approach, there's no real compaction happening. The SST files are just purely ordered by time. It's just basically level 0 of RocksDB. When the database reaches a maximum size, the oldest SST files are deleted. That works for our use cases because of our batch computes are generally writing much of the same data every day, just updating values. So the old data is not worth it to us. But the downside is that a read may access every single record in that level, the level 0. And that's in the worst case, and that's illustrated by the diagram, where in case you're accessing 4, 5, and 6, if that record is not there, it has to go through all of them before it knows that it's not there. It could be surprising that we can get a low latency using this approach, because we are accessing every single file. Sometimes some data needs to be read and checked to see if it's there. But we use other RocksDB features to optimize this. And probably the most important one is a full file bloom filter. So the full file bloom filter will prevent most of the SSTs from being checked or being accessed on disk. Without it, if we didn't have it, most likely the small number of application requests would maybe saturate the disk just from accessing all these SST files. The other thing that we do is we pin the bloom filters and indices in memory so that we don't accessing the bloom filters and indices does not require a disk access. So the downside of using FIFO, one downside of using FIFO is that when we use the full file bloom filter, we have to make the bloom filters be even larger than we would if we had used level compaction. That's because because the overall set of bloom filters is less effective because you have to access multiple files. And so we're trying to prevent as many incorrect disk reads as possible. So we just have to enlarge it even more. So I think a normal configuration for level compaction might be target 1% false positive rate. I think for us, we try to target even like 0.1 or 0.1% or something in that range, so that when they combine it together, it reduces the disk access enough. Oh, and it's the same diagram. So another optimization that we use is to actually create multiple RocksDB databases on a single server node. We partition and shard the records across all those RocksDB databases. So the goal here is to reduce the number of files that need to be checked on any single read request. And then reducing the number of files results in reducing our worst case read request latency. So as I mentioned earlier, we have optimizations based on region locality. Since many of the users the requests are directed to a single region, that they're usually the closest region to them, the user's data is normally only accessed from that single region. But we are using our replication system, we are replicating that data to other regions just in case we have to do a failover or some other use case. We can take advantage of this this normal use case of data being only accessed in a single region by keeping the remotely replicated data out of our local memcached process. We don't really need that data that often, and if we need it, it will be on disk. So in this case, we'll be able to keep the working set to be a kind of a data center specific working set, and it allows it to fit in memory. So we implemented this by creating a separate network port that we call the batch port, and that's used by the cross-region replication system. What happens is that the write requests on the batch port doesn't modify memcached unless the record already existed in memcached before. So this is where separating memcached and RocksDB into separate layers basically helps us. There's less thrashing of memory in memcached, and it makes the memcached queries more effective. So the diagram is created to try to illustrate a very simple point to kind of make a point to make it simple to understand is that what we're doing here is like what happens if you're writing a unique record. The record doesn't exist yet on the server. So if a record is written on the standard port, which is usually mostly used, it has to update both memcached and RocksDB. The write to memcached there, though, may result in memcached having to eject another record, and that record may be something that was useful for us, so that generally would reduce our effectiveness of the memcache's effectiveness. If you write on the batch port, though, would only update RocksDB, and you can remember that this is a new record that isn't there. It still has to do a check to memcached, but if the record's not there, it doesn't change memcache's memory. The write to RocksDB has to happen, and it just basically this approach makes the memcached queries more effective. It keeps our majority of our reads faster than they normally would be. So FIFO compaction is not a good fit for all use cases. It works for us in some of our use cases, but there's others that we do not use this for. It's not suitable for use cases where you have some records, a subset of records, more frequently updated than other records. The diagram kind of illustrates this point is that the records on the darker blue, those are the older records. They're written some time ago. But then the records in the lighter blue, the records A and B, you can see that it's A1, A2. What that means is that it's basically writing A and B records over and over again. And so eventually, if that continues to happen, the records eventually on the older records will eventually get pushed out, but we still want them. It's actually incorrect behavior. For our use cases, it is not an issue for us in our use cases so far. We do want to eventually be able to solve this case, but without some sort of compaction mechanism or server more smarts in figuring this out, that this is something that we live with for now. Another issue is that the expiration time in records is actually implemented by our mnemonic layer. RocksDB does not know about the expiration. What happens is that the RocksDB will return a record if it has it, even if it's expired. And our mnemonic layer has to drop the record. Generally, that means that RocksDB is doing more work than it would need to if it knew about the expiration. And then, of course, the latency is generally higher in that case. It's something that we live with for now. And I mentioned before that we require larger Bloom filters with the FIFO compaction. So I'm going to go over some performance numbers in the next few slides. So just to set that up, this is the AWS Instance Type that we use. Generally, you can see that the number of CPU cores is small. The amount of SSD disk space is quite high compared to the RAM. The one thing is that to remember that when we switched to Moneta, we had to use this instance type. And so when the instance type that we were using before had a lot more memory, but also had a lot more CPU power. And that is actually becoming a limiting factor for us that we have to worry about. So this is just a benchmark. In a few later slides, I'll show you production numbers. This is a benchmark that we start with to understand the behavior in bad conditions where hit rates drop more than we expect or the traffic is much higher than we expect. In this case, what we have is actually 3 sequential runs of a load test. You can see where I restarted the test. That's just an artifact of having that load test behavior. The general hit rate here is actually, the L1 hit rate is only 60 or 70%. It's actually fairly low for us compared to production. And our overall hit rate is 80% here. That's also very low. The test writes about 140 gigabytes per each run. So generally, you can see that the latency numbers are here. There's actually 2 graphs. These numbers, the latency numbers, are using this axis. And generally, they're low. This is about 6 milliseconds on this line. You can see the 95th percentile is this blue line. And it's fairly stable, but you can see it's kind of increasing slightly. The 99th percentile, you can see the upslope is more noticeable. And it kind of sort of correlates with this green line, which is the number of accesses to the RocksDB layer. But it's still not clear why that is, so we have to look at some other metrics to dig a little deeper. So this has just the latency numbers of the overall latency plus the L2 latency. You can see it's mostly the overall latency is dominated by the accesses to L2. They're pretty much correlated, but it is unusual that they continue to increase as the test goes along. And it also, with each test run, the starting point increases just a little bit more on each test run. So we'll get to figure out why that is in a couple more slides. So this one has also, there's 2 graphs kind of superimposed on each other. The green line, or actually no, the blue line is the CPU usage on that box during the run. The green line is the overall number of requests, and the reddish line is the requests to L2. You can see the CPU usage is also increasing as the test goes along. And so that there seems like there's a bit of a correlation between the latency increasing and the CPU usage increasing. But it's not really sure there's a cause and effect. Yes? I'm sorry? So the write load stops right here. The reload is constant. The write load stops here. It started here, so that's about 10 hours. Yeah, it's about 10 hours on every single run. Unfortunately, I didn't finish the last run because I finished the load test yesterday, and I started running it on Monday. But anyway, yeah, it's about 140 million, 40 gigabytes of data being written on each run, 75 million records for each run. So this one actually should show you the actual cause. The CPU usage is increasing while the number of SST files is increasing in the database. You can see in each run it continues to increase because I'm not dropping any data. I'm continuing the runs just like we would do in production. And so what's happening is that basically the read requests have to go through more files over as the database fills up. It has to go through more and more files, and so it increases the CPU usage and increases the latency. Yes.
Does it get to a plateau after a while?
It will plateau when the database is full. Basically, the database is probably full around that far right. Because the thing is that what RocksDB's FIFO approach does is that it's only deleting based on the data size. It doesn't know anything about the data. It doesn't know anything about like when it can delete an expired record, and doesn't know anything about whether it can delete with FIFO, it doesn't know if there's a duplicate record yet. So we have something that we're going to look into to figure that out. I'll go over that in a couple of slides later. But if we go back to these latency numbers, this is really worst case for us, and is most likely we haven't seen it happen. But these latencies, one is our L1 hit rate is very high, And the other is, even with these numbers, this is actually within our bounds of what we want at this percentage. The average is very low. Even 95th percentile is still very low for us, for our use cases. It's 95th is down here. It's like 1 millisecond. So here's some. Sorry, I think I skipped too much. Okay, so this is our production numbers from our batch system. This is the batch pre-compute system, and it's the accesses are done. The read accesses are done for online requests, but the data is loaded in a batch process that's run daily. And generally, we can see that the latencies 95th and 99th stay below 1 millisecond. The records are about 20 kilobytes in size on average. You can see that the 95th and 99th% latencies are sort of closer to the L2 latencies than the L1. And that's primarily because the L1 hit rate is only 90%. So that's expected for us, because what happened is that we deployed the Moneta for this, and then because we can store so much data on a single instance because of the SSD, we shrunk the cluster size. And so even with this level of this latency number, even this latency number is acceptable to us. So this is our cache that actually is serving high volume number of requests. It's actually a more dynamic online request system, and the data is not generated offline. In this case, the records are smaller though. The latency here is also below 1 millisecond generally, but you can see that the overall latency is closer to the L1 latency, and that's because the L1 hit rate is 97%. That's expected because we just deployed this about a month ago. We just replaced our previous cache with this Moneta cache, and we have not had the chance to shrink the clusters yet. We eventually will, and we would expect the L1 hit rate to drop because we're going to have less memory available in L1. And these are some more latency numbers that kind of provide the full spectrum of latencies for that last cache that I just showed you. So how much did we save? So on average, we saved 70%. That's from a combination of using a different AWS instance type that is generally cheaper, and also reducing our cache cluster sizes because we're using SSD. So, okay, although we've gotten great results, we have some limitations. I'm going to go through this real quick. We have less visibility. We don't, because of the fact that people doesn't delete duplicate records or expired records, we're going to, the overall data size is unclear to us. That's compared to our Memcache deep servers from before, we had the exact number. We have to restrict the data size on caches that are used for our pre-computes to only half of the configuration so that we don't lose any records temporarily. We generally have a lower max throughput than our Memcache based servers because we have less CPU and we have to access disk. Let me see. We have to just plan better when we deploy than we do with Memcache. So our future is that we're going to try to investigate blob storage feature that is available to that's being developed on GitHub now by Facebook. The idea here is the hope is that we're going to require less read and writes to the SSD during the level compaction phase, and that will allow us to use level compaction, and that will lower our latencies, and it will give us a higher throughput, lower our CPU also. Until that feature is ready, what we're going to do is do some shorter-term changes. We're going to put some more smarts in to be able to purge some of the expired SSDs earlier. So this is going to be useful for like the last production use case I showed you, which it has the relatively shorter TTL use cases, where we'll be able to expire. You can purge about 60% of the SSDs earlier than the FIFO compaction, and it should reduce our worst case latencies. And it just what should give us also a very precise number for the amount of data we're storing. It doesn't help our batch compute caches though, because batch computes there's going to be a lot of duplicates, and the duplicates are not expired. So we're going to have to figure out another way to dedupe and drop the duplicate records. And so EVCache and Rend are already open source. Mnemonic is not yet open source. And that is all for our presentation. Thanks for listening. You have any questions? Yes. Yeah. We hope to. In production right now, we are mainly using Rend and RocksDB and with special configurations. And so we're not providing a lot yet as far as extra value. But with the extra logic that we're going to add, which is the SST purging of expired records and also some way to dedupe records off a little bit more cheaply, then compaction, I think we will try to dedupe. We will try to open source it sometime this year. Yes.
Are you using any compaction filters?
No. No, I don't believe the compaction filters would execute with FIFO. I think I may be mistaken though, but I don't believe they would execute.
And regarding the personalization that you showed in there, are the clients running on the same host?
No. The remote.
They're remote?
Yeah. No, the network hop is not included. These are server-side latencies to the point where just before we would send it off to the network. It's only server-side. We can't measure the client-side because most of our client-sides are, we do have measurements for our client-side. It's just that our client-side clients are mainly Java. And then with Java, we have all these GC numbers that we can't figure out what's causing what.
It's just a server-side latency.
Yeah, only server-side.
What was the requirements for you to choose something else, or what made you choose?
So we have a fairly high write load, so we need to be able to handle that write load. I was trying to keep I wanted the appending feature of style of LSM feature of appending data and only appending. I didn't want to have to do like using B trees where the data gets overwritten because that causes problems for SSDs. And there's you can do that and it looks kind of fast initially, but I think with SSDs, eventually the SSD itself has to do its own garbage collection, and using B trees would be somewhat problematic. So I wanted something that was somewhat cheaper. And so using LSMs, the writes get buffered, they get flushed to disk and a batch, so that makes it faster. Reads are somewhat slower, but given that most of our reads are handled by memcached, it's less of a problem for us in that case. I did not have the time. Unfortunately, the RocksDB is very configuration intensive, so it took me a lot of time to go through understanding the level of compaction behavior and then deciding that I couldn't use it. And then when I found FIFO compaction, it worked well. Unfortunately, I didn't have time to go through the other databases.